let me press record. In this tutorial, we're looking at chapter 3 in the algebra book, which is mostly complex numbers. Now, it's crazy. The number of questions for this week is like 85 questions. And so obviously we can't do all of those. But what I usually try to do, I start with some of the earlier questions, like in today's tutorial, and then I move through to the later questions, like on Wednesdays and Thursdays and stuff. So if you want to get a whole bunch of different questions, you can just watch the recordings. Okay, so let me have a look at this PDF. Now, just to remind everybody, this is a tutor-led tutorial. So that means we'll be working through some of the questions together. So this is chapter 3. Let me just go up so you can see what it is. Hang on, page 118. And I wanted to start with question 7. So remember, complex numbers have a special form. Here we have the so-called Cartesian form. And the most important thing here is that the I is the imaginary unit, and it's basically defined as the square root of -1, which is crazy, right? Now, when students see complex numbers, they go, wow, it sounds complicated because it has the word complex inside it. But really, what complex numbers try to do is simplify things in an amazing way. So don't be fooled by the title. Okay, so let's start off with some basic ones. Here we've got the following general Cartesian form, and we want to simplify these expressions. Okay, so let me share my screen with you, and we can have a look on the document camera. So the most important thing is don't freak out, right? When you see complex numbers, some students go, oh, it sounds so complicated, but actually it's pretty good. Okay, so question 7. All right, so A and B here are just real numbers. I is defined to be the square root of -1, and we want to simplify the following expressions. So let's look at z squared. Okay, so pretty easy. I'm sure you all know how to do this. But just for the record, let's, yeah, Rahul, I've got the Sharpie back today, buddy. Yeah, I'm quite liking that. Let's expand this. And the most important thing that you can really note with these sorts of things is that these two expressions here. Okay, so yeah, so now you're on it. So we square that. So it's going to be a squared plus 2 times abi plus ib all squared. Okay, and so with the I squared equals -1, this will actually become -b squared. All right. Rahul's on it. Okay. So this would be the Cartesian form, if you like. There's the sort of the real part, and there's the 2ab is called the imaginary part. Okay, so pretty easy. These are just the basic things. You don't really use this, but this is how I is defined. You use this first part a lot. Okay. All right. All right, so that's an easy way to start week 7, Monday morning. Let's get a little bit more difficult. So let's consider that. 1 on Z. Now, this is a little bit interesting. You can do this problem a couple of ways. What I like to do with these problems is to simplify the notation as much as possible. Okay, so when you're working with this sort of form, when you have got a division going on, what's helpful is to use what's called the conjugate, right? So what you can do is multiply the top and the bottom by this conjugate, right? So if Z is this, then this notation Z bar is just A minus IB. All right, so that's called the conjugate of Z, or Z bar. And why do we choose that? Well, the bottom part is actually going to simplify really nicely if you make that multiplication. Okay, now geometrically, if you have a point, this is Z, then you reflect it in the horizontal real axis to get the conjugate. All right, so doing this, what are we going to get? Well, on the top, we've got Z bar, and down the bottom, we've got Z times Z bar. Now, can anybody tell me how can we simplify the bottom in terms of Z? Does anybody know? Smash that chat button if you can tell me. Can we actually simplify that? Notice I haven't written A's or B's or anything. Good question. Good answer, Julia. Yeah, yep. And Cameron, yep. You're on the right track. So one way to think about it is to write the product of these two things as the square of the magnitude. So basically, if you look at this picture up here, which is tiny, of course, that distance there to the origin is this magnitude of or modulus of Z, right? Now, notice I haven't put any A's or B's in there yet, but in the comments, you guys are doing that, which would be the next step. Okay, so what is Z bar on top? That's going to be A minus IB. And down the bottom, what is the square of the length? People have put that in the comments, just using Pythagoras. It's A squared plus B squared. Ta-da! So rather than putting in, A plus IB down here and then working out the conjugate, you can just keep it nice and compact if you want to. Okay, I quite like doing that. All right, part C coming at ya. All right, so let's consider this thing here. And this is another one where we're going to introduce the conjugate. Now here we're obviously excluding the case where we're dividing by 0. So based on the previous example with this multiplication by a factor of 1, let's take the conjugate here and multiply. And you'll see some nice, or you'll be reminded of some nice properties of the conjugate, Z minus 1. Okay, so I'm going to put a conjugate in there and a conjugate in there. Okay, it's not an equal sign. It's not two divisions, the conjugate and the conjugate. Okay, so who can tell me in the chat, is there a way of breaking up this and simplifying it in the top? Does anybody know? What would conjugate of Z minus 1 simplify to? Oh, not interesting, Rahul. Not quite. Oh, very interesting. Okay, Heike is saying z squared minus 1. This is interesting. And now Rahul saying z conjugate. Well, you're kind of close. Why the plus 1 though? Because you can see the real part doesn't change. And negative 1's real. So the way I would do it is say, okay, you can actually break this down into two parts. So when you have something like this, you can break it up. I'm not going to touch the bottom. Oh, sorry, that should be a minus. Okay, and I'm going to keep that there. Now, what is the conjugate of negative 1? Negative 1's just here. So the conjugate of a real number is just itself. Okay, so we'll get z plus 1 times z bar minus 1 all over, and I can just use this thing here, that, because I'm multiplying this thing with the conjugate of this thing, okay? And I know from down here that that's just the square of the length. Okay, so this is, you can see this is a little bit more complicated, but it brings everything together involving, you know, conjugates and stuff like that. So let's expand this. Z times Z bar minus Z plus Z bar minus 1 all over this. Now, I'm not going to touch this because that's pretty simple there. And I'll leave it till the end. So now, what is Z times Z bar? Well, it's the square of the modulus of Z. Okay. And what is this? I can actually simplify that a bit. Okay. I can actually simplify that a bit. It's going to be 2i times the imaginary part of Z minus 1. Okay, so if you look at the imaginary part, there's like formulae for the real part and the imaginary part, okay? And so what I've done here is I've just gone from there to there. So why am I not using A's and B's? This is far easier than using A's and B's. And now we're in a position to actually do it. Okay, so let's put the A's and B's back. So that is here. Okay. Who can tell me what's the imaginary part of our original complex number in the chat? What's the imaginary part? Yeah. So Rahul, so you forget about the I. The imaginary part is just this thing here. Okay. So that's the imaginary part of Z, and this is the real part of Z. Okay. So you don't include the I. Yeah. Thanks, Aishi. All right, so minus 2 times I times the imaginary part, which is B, minus 1, all over this. Okay, so it's going to be A minus 1 all squared plus B squared. Okay, and you can bring that over here if you really want to. That's the real part. Da-da-da. Ta-da! Yeah. Awesome. Awesome. Okay, just remembered that I don't have any toys in the background, so I'm going to put this little snail in. Yeah. So what I try to do with these problems, it's okay to put the A's and the B's in straight away, but I actually try to use the simple identities of conjugates and stuff to simplify it. And lastly, you put in the A's and the B's. Otherwise, it's quite easy to make a mistake. Yeah, I agree. It's easy to make a mistake. All right. So what do you think? Any questions? Any comments? Let me know in the chat, people. Smash that chat button. Let me know. All right. So this is kind of your entry level stuff. Part C is obviously more difficult than part A and part B. Ah, Darren, yeah, it's an interesting question, Darren. Thank you for asking. So let me show you. Let me show you. So Darren has asked about there's two important relationships here, right? So yeah. So if I have a complex number, Z, okay, the real part is that, the imaginary part is that. And what, like a formula like this gives you, it sort of gives you a relationship between the conjugate and the complex number. Okay, so I put these two things in the previous slide. Okay, and so let's work out how we can build these some formulas for real Z and imaginary Z, right? Imaginary part and the real part. Okay, if I add the conjugate to Z, watch what happens, Darren. So if I add Z to Z bar, what happens? The IBs cancel and you get 2A. So if you divide that by 2, you get A. You're following so far, Darren? If I add Z plus Z bar, I get 2A. And then to just get the A part, I divide by 2. Okay, what about this one? Well, instead of adding, we want to end up with a B. So let's take away. So Z minus Z bar, the A's are going to cancel. IB minus negative IB, so 2IB. And to fix that up, you're going to get divide by 2I. So all I've done in the previous question is bring that to the other side because we had Z minus Z bar. Okay, so if I show you here, let's see if I can squish it in. You can see here that's this is kind of 2I times the negative of that. So that's where the negative sign comes from and the I slips in there too. So Darren, are you kind of, I know it's a little overexposed. Let me turn that off. That's probably better. Sometimes when I put my hand in the screen, it freaks out a bit. So Darren, is that starting to make a bit more sense? Cool. All right, so there it is, people. So that's how you get it. All right. Let's keep on going. Okay, Zia, question in the chat. Can I confirm that the -1 only applies to that A in the denominator in part C because it is a real number? So the negative. So which line are we talking about here, Zia? First line, second line, third line, fourth line? Yep. In the denominator. Correct. Yeah. So if you look, if Z's that, what is Z minus 1? It'll be A minus 1 plus IB. Yeah. Rahul's on the case. And that's right. Yep. Excellent. Excellent. All right. Let's move on to a different question. Okay. Yep. So here's another one. I'm going to put up the PDF in a second. Let me just pull out a question here. Yep. Okay, let's have a look at the polar form. Okay, so the polar form sounds very cold, but it's another way of writing the complex numbers. So here you can see we've got two axes, the horizontal real axis and the vertical imaginary axis. There is another way of describing and representing complex numbers. It's called the polar form, okay? Polar exponential form. Okay, so let me share my PDF and we can talk through that. Okay. So here it comes. Yep. So find the Cartesian form of the complex numbers whose moduli and principal arguments are these things. So this tells you that we want a complex number whose modulus or length or size is 3, and this principal argument, which is an angle, is pi on 3. So let me just draw a quick picture because I think that that's a good way to understand these problems. Okay, so I'll go back to my document camera and we can have a little look. Okay, so in this question, we've got yep, the modulus of a complex number is 3, and the principal argument is pi on 3. All right, so the way that I like to write complex numbers, I put a little tail on the Z, but I don't do that when it's a number 3. Okay, so you know, some people on YouTube go, "Oh, your Z's look like 3s." Well, yeah, that's sorry. All right, so let's draw a picture and try to work out what's going on. So here's the real axis. Here's the imaginary axis. Yep. And we put a complex number in here. This length is 3 units. And this angle is pi on 3 radians. Okay? And what we're trying to do is work out the coordinates of Z in terms of the Cartesian parts. So you can see I've actually got a right-angled triangle here. It's pretty easy to do. So, you know, you want to work out this coordinate here and this part here. So you just want the B here. Okay. So you can do this a number of ways. Yeah, Zia, I'll explain the difference in a minute. The capital letter makes a difference, right? So just using trig, we can get A to be 3 cosine pi on 3, and B to be 3 sine pi on 3. Yep, okay. So, you know, pi on 3, 60 degrees, it's not hard to work out what's going on there. So it'll be 3 times a half. This will be 3 times root 3 on 2. And so our z is just going to be, well, I'll factor out the 3. And there you have it. Okay. Let me darken that image a bit, see if we can stop the, oh, I think that's better. Okay, tell me if it's still overexposed. I've just changed the setting on my document camera, okay? Yeah, I think that's better. Okay, so what about, so Zia, your question is great. Let's have a battle. So arg of z versus arg of z. Okay, now the most important thing, this is always between negative pi and positive pi. So that's probably the most important thing. Whereas this, that can be sort of, you know, any value. Okay, so if I was to say, you know, let me draw a picture here. Let's say I had if z equals 1 plus I, right? So I know where that is. It's somewhere in there. Yep. Okay, and the angle is going to be pi on 4. And, you know, the length is going to be something like root 2. Okay. So when we calculate the principal argument of something, we always want something between negative pi and pi. Okay. So let's say I wanted to calculate the principal argument of this. Yep. So that would mean go out there and then do another loop. So that's actually, sorry. Hang on. Consider, yeah, it's not writing that very well. So if you go out there and then do another loop, you actually get back to the same complex number, right? It's the same complex number. So if I want to take the principal argument here, it's going to be the value that's between negative pi and pi, right? So it doesn't make sense to have something like, you know, this is like going to be, right? It doesn't make sense to take the principal argument and end up with a value like that, because that is not between negative pi and pi. Okay? So when we're talking about principal arguments, Zia, we're always showing that or wanting to find a value that's between negative pi and pi. Does that make sense, Zia? Okay, so that's the most important thing. So there's only one principal argument, but there's many. There's only one arg, but lots of little args. Okay, so this is unique. There's only one. All right, so I hope you get, not a very good explanation here, but I hope you get some idea. All right, let's go back to the PDF. Oh yeah, all right. So I'll put that up in a second. Let me just have a look here. Okay, let's have a look at 24, and I'll put the PDF up. Okay, so it's a H1, but actually this is not a very hard question. So here it is. And they give you a hint. Use this identity to prove this more complicated identity. Okay, so Z1 and Z2 are complex numbers, and let's see how we can smash this one out. So I'll take a new page. All right. So I'll go back to my .cam. All right, here we go. Okay, so consider. So this is essentially the left-hand side of the identity that we want to work with. Okay, so let's use the hint and break these down to products involving conjugates. So I can write the first term as this product and the second term in a similar way. Yep. And what I'm going to do is to break up the conjugate of this sum. So this is just Z1 bar plus Z2 bar. And same here, Z1 bar minus Z2 bar. So this is just a nice property of the conjugates involving complex numbers. Yep. And now let's expand, and we can hopefully see some explanations and some simplifications. Okay. So we're going to get Z1 times Z1 bar. Well, that's going to be Z1 bar squared. Z1 times Z2 bar is going to be that. Z2 times Z1 bar, and that's going to be Z2 all squared. So that one times that one, and then you're going to get some cancellation going on down here. So Z1 times Z1 bar, Z1 squared minus Z1 times Z1 bar, Z2 bar. So you can see that's going to cancel. Okay, same here. And you're going to get that. Okay, so now you're going to get some cancellation here. So cancel, 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 cancel. You're going to get two lots of that, and then you get the right-hand side. So Rahul, you think it's easier to expand first. Is that right? Am I getting you, am I on the right track there? So you think it's easier to expand first? You want to expand those things first and then move to it? I think this is great because you're learning the conjugate properties as you go along. But of course, there are many ways to do it. Well, Osman, it's a good question. Why did I put a full stop at the end? Because I started a sentence here. with a capital letter. So consider this equals this equals this equals this, full stop. That's the end of my thing. Does that make sense, Osmond? Yeah. So I don't usually like to leave things hanging, but I do. If you look at my other one, my previous one, you can see let that equal that. We have that, full stop. Yeah, full stop. I like using full stops. And in fact, that's one of the things in your assignment. Are you asking because of the assignment, Osmond? It's a good question. It's a really good question because these are the kind of things that are helpful in communication. And when you type your assignment, they'll be looking for things like full stops. So it's a really good question, Osmond. You know, if you don't put the full stops in your assignment, you'll lose marks. Does that make sense? Yeah. So it's a really good question. Okay, so that's a simple way of working with the conjugate and stuff like that. Even though it was a H question, it really wasn't that hard, right? So yeah. So I'm going to do maybe two more. I want to move ahead to I think it's 26. So let me yeah, 28. Okay, so keep those questions coming in the chat, people. I'm loving this. I am loving it. So let me, oh, hang on, shared the wrong screen. Ba-bow. Let me go back and share the correct PDF. There we go. Okay. So it's taking a little while to share here, but I thought we could look at 28. So 28 is an interesting one because you've got a polar exponential form of a complex number and a Cartesian form. Okay, and we're asked to calculate the real part of this mess. So let's go through that and see if we can find the real part of that mess, and then we can unpack it and have a look. Okay. All right. So let me go back to my document camera. I need the hotkeys so I can do fast transitions. All right. So this is 28. All right. Okay. So we've got Z in this polar exponential form, which is a length and an angle. And we've got another complex number, which is in Cartesian form. Okay, so let's put this together. Let's consider this thing here. So this is I times W plus Z bar squared. And we're actually then consider. So we're going to actually, we really want the real part of this, whatever it is, okay? But I'm just going to start with this form and then we'll take the real part in a minute. So I times W is going to be this. You could of course convert these to the same form, but I don't think it's actually necessary here. Okay. Now, what is the conjugate of Z? Well, like I said before, all you're doing when you take the conjugate is sort of reflecting in the horizontal axis, right? So if I take the conjugate of that, all I do is I change the sign on the angle. So that's it. Yeah, Zia, it's a good question. Are there any worked solution to the course pack questions? There might be some on the web. I don't know if the school provides them, but there are lots of YouTube videos with solutions. Yeah, have you seen the YouTube videos, Zia? Because there are lots. So every question that has a V next to it has a YouTube solution. So if you look in the PDF and you see V, that means there's a YouTube solution. So there are lots. Okay, so that's usually pretty helpful. So yeah, hopefully that works for you. Okay, so what about this thing here? We're going to get, what are we going to get here? We're going to get I plus I squared. So I squared is -1. And over here, what do? It's going to be 3 squared times e to the, and you multiply 10 pi I on 6. Okay. Yeah, now we're taking the conjugate here, right? Negative. Okay, so so now, where is this going to take us? Okay, where is this going to take us? Well, let's see. Negative. Oh, you're right, I did forget. Hang on. Just give me a second, everyone. Yeah. So it's going to take us all the way around there. And we're going to stop there. And this angle here is going to be -pi/3. Thanks, Osmond. Okay, so if we want the real part of this, okay, so I've just changed that now to get the smaller angle between -pi and pi. The real part of this okay, so what's the real part? Obviously, that's not going to be part of it. That's going to be part of it. And what's the real part of this? It's going to be -1 plus 9 cosine pi/3. Oh, well, I guess -pi/3, which is the same. Okay. All right, you know cosine's positive here, so these things are going to be the same. So this is a half. So we'll get something like 7/2. Okay, so going from here to here, remember I just used a simple idea, but a very deep one, called Euler's formula. Okay, so I know that this for example, okay, so this is a very important formula called Euler's formula. And so if I just want the real part of that, you can see it's going to be this first bit here. It's not going to be this second bit. So that's where this thing comes from. Okay, so Euler's formula is super, super important, and you use it all the time. And you know, you can get it to go, for example, from the polar exponential form to Cartesian, and it's just an amazing formula. Okay. All right, questions, people? Hit me up with your questions. Smash that chat button. Let me know what you're thinking. There's been some great questions so far. And also, Zia, have you seen the video solutions? So if I go back to the PDF, right? Like I want to show you something here, Zia, because it's important and it goes back to your question. Okay. So where is it? Is it here? So there, can you see the V? Yeah, yep. So there it is. Oh, yeah, conjugate. So there you go. Yeah, no worries, Zia. My pleasure. All right, Rahul, let me have a look at your question. So I'll go back to, yeah, I know, Zia. This is what happens, right? Usually the questions that you want aren't there. Okay. So let's have a look at working out this angle. It's a really good question, Rahul, and I make mistakes too, right? So let's go back here as well. So let's look at just this part here. Okay, so if you have e to the 10 pi I on 6, right? And so you can simplify that down to e to the 5 pi I on 3. And now this is almost 2 pi I on 3, right? So that's like almost, it's almost a full rotation. Okay, this bit is almost 2 pi, but you can come back pi on 3. Okay, and because you're rotating clockwise, it's a negative. You want the negative there. Okay, so Rahul, am I kind of making sense there? The way I did it was, I in this case, I just simplified and I realized, that's 2 pi, and then just take away pi on 3. Well, because 5 pi on 3 equals 2 pi minus pi on 3. Yeah? If it was a full 2 pi, you would go all the way around. But it's not quite that, right? Because you've only got 5 pi on 3 to play with. You got it? So the way I think about it is, maybe I go here and go a little bit up or down. Maybe I go here and go a little bit up or down. So that's the way I like to do it. It's a really good question, Rahul. And if you get that angle wrong, which I do sometimes, then the rest of the question is not going to work out a lot of the time. So yeah. So it's important to pay attention to, and I get it. Right? Yeah. Yeah. Yep. Or yeah, that's right. All right, folks. I think that is enough for today. So it's been great seeing you again. I hope week 7 is going okay. And yeah, I was pretty excited. I was a bit lonely last week. I was like, what do I do again? I usually teach some classes. So it was a shame not to see you, but I'm glad that we're back. And just enjoy the day, everyone. Enjoy the week. And I will see you next week. And like I said, later on, I'll do some more solutions in the shoots to come. So thanks again. Share. And enjoy the day. And I'll see you next week, everyone. Bye.